All right, ladies and gentlemen, good morning. Class recording has started, so we're good? Yep, okay. All right. Earlier this week, we introduced the concept of energy, and we talked about what we're going to use as our working definition of energy. How do we define energy? Kind of good. The ability to do stuff, right? The ability to do damage, the ability to move or change things, make them different than they were before. We talked about the idea that energy is represented by the unit joules, but joules is a derived unit that is a combination of base units. And we saw yesterday when we were doing our calculations, even though you can't see it on the screen recording, that this combination of base units, right, kilograms times meters squared over second squared, things cancel, leaving us with the unit that we want for mass or speed or whatever we're solving for. Okay? We talked about mechanical energy being a combination of three types of energy, those being kinetic energy, gravitational potential, and elastic potential. We spent a bunch of time talking specifically about kinetic energy and the factors that affect it, mass and speed, and we talked about how those relationships work, mass being a direct relationship, speed being a quadratic relationship, blah, blah, blah. If kinetic energy is energy of motion, potential energy is energy of position. Where something is allows it to do or change or move something than it could before, right? Most of the time we're going to talk about gravitational potential energy, and that gravitational potential energy depends on three factors, right? The mass of the object, the height that it is above the ground, and then we use that lowercase letter g to represent the effect of gravity. Here on Earth, we summarize that effect of gravity with 9.81 meters per second squared. Good? Okay. Now, let's talk about this concept of work. Okay. Let's say I take this baseball, right? And I hold it, I don't know, 1 meter off the ground. Okay? And then I'm not going to do this, but if I drop it, and let's say I just happen to drop it and it hits my foot, it's going to hurt. Yes? Yeah. We talked about the idea that if we took this baseball from a height of 1 meter to now 2 meters, what does that do to the amount of potential energy that that the baseball would have if we lifted it from 1 meter up to 2 meters? It's double the amount of potential energy. All of the factors that affect potential energy are direct relationships. So if we go twice as high, we have twice as much potential energy, right? If I drop the baseball from that point, how much is it going to hurt when it hits my foot? Twice as much, right? Twice as much potential energy means twice as much ability to do damage, to hurt things, to change things, whatever, okay? But do I have to lift the baseball up to that height? Sorry, stupid question. Will the baseball go to that height on its own? No. Something has to make it go there, right? Either I have to physically lift it or I have to throw it into the air. But in either of those two instances, what happens to the energy of this baseball? Let's just go general, right? If I toss it into the air to a height of 2 meters, what happens to the energy of that baseball? Does it go up or does it go down? It goes up, right? The higher something goes, the more potential energy it has, okay? Kendall, that relationship of how fast we have to throw it is a little bit beyond what we're going to do in this class. That's more of a physics thing, so let's not worry about that too much. Let's just go more in terms of, does it get bigger, does it get smaller, right? Will the energy of this baseball change if I just put it down on the counter and leave it here? Will the energy of this baseball change if I put it on the counter and leave it there? Will it go any higher? No. Will it go any faster? No. If we don't do anything to it, its energy stays the same. But by doing something to it, and when I say doing something to it, we're going to talk about what that means in just a second, I can get that energy to change. And that's where we get into this concept of work. Okay? Work we define as the the outline that we filled out on Tuesday. This is the back of the outline that we filled out on Tuesday. So all the kinetic and potential energy stuff, this stuff is on the back of it. Okay? Work we define as the transfer of energy between objects. If we are transferring energy from one object to another, that means that the energy of an object is going to change. The energy is either going to increase or it's going to decrease when we do work to it. Okay? Or work on it. Are we good with that definition? Okay? So keep these two things in mind as we move forward and we start analyzing more situations. Okay? In order to get the energy of an object to change, two things have to happen. First, we have to apply a force to it. As we discussed, this baseball won't do anything different sitting on the counter by itself. So to get it to do something different, we have to apply a force. But then, even when we apply force to something, sometimes nothing happens. So in addition to applying a force, we also have to move that object. So in order for work to be done, we have to apply a force, and we have to move the object with that force in order to get its energy to change. We summarize that idea with this equation down at the bottom. W equals F times D. What do you think the W is going to stand for? Work. What do you think the F is going to stand for? Force. And what do you think the D is going to stand for? Distance. So we can get work done on an object if we apply a force to that object and it moves because of the force that we apply. Okay? Good? All right. That concept is what's going to take us basically through the rest of the day. So, for the rest of the day, we're basically going to answer one question. Is it work? Okay? Ready? Here we go. Question number 1. When a pitcher throws a baseball, you guys don't have that picture on your sheet, but you have a picture of somebody throwing a baseball. When the pitcher throws the baseball, is it work? Yes or no? Yes. That's the first thing, okay? So yes, this is definitely work, okay? So we said there's sort of two ways that we can rationalize or explain that work is done, okay? Somebody tell me how we know this is work. There's two ways we can think about it. Ethan, what's one way? He's applying a force to the baseball, and what does the baseball do because of that force? It moves, right? He starts applying a force back here, he moves the baseball here. That's one way that we can explain that work is done. So first, yes, right? He applied a force to the baseball, and the baseball moved because of that force. Okay? What's another way that we can explain that work was done? If we go back up to the very top of the page, we said that work is the transfer of energy, but what happens to the energy of an object if work is done to it? The energy has to what? Let's go more general than that. Does it always have to go up? It has to change, right? Does the energy of this baseball change? Yeah. Specifically in this case, Kendall, it's going to go up. what type of energy goes up for this baseball when the pitcher throws it? It ends up with more what? Well, what does it do after he throws it? What type of energy is this? It's kinetic energy, right? The pitcher increases, sorry, buddy. That's metal, so it makes that like banging noise. Right? The ball has more kinetic energy than it did before the pitcher threw it. Okay? So we can explain it two ways. One, we can explain that the pitcher applies a force and the ball moves because of that force. Or we can say that the kinetic energy of the ball increases. Okay? All right, good there? That's the problem with that spot, is that you can't see the bottom part, but now you can, so there you go. All right, good there? We okay with that picture? Picture number 2. A girl using a pulley to raise a crate. Is this work? Yes. Okay? So yes, this picture also describes a situation where work is done. Again, we can go with 2 ways of explaining that work is done. Ethan, what's one way? It could, but in this case, if we're talking about the crate itself, right? What's happening to the energy of this crate? Got somebody to take it over? What type of energy specifically is changing in this for the crate in this picture? It's increasing gravitational potential energy, right? It ends up with more gravitational potential energy at the end of this situation than it had at the beginning of this situation. So that's work. Okay? What's another way that we can explain that work is done? We said in order for work to be done, we have to do what to an object? Well, we change its energy. How do we do that? Apply a force, and then what does it have to do because of our force? Move, right? Is the girl applying a force to the crate here? Through the string, but yeah, right? Through the rope. So the rope is pulling on it, and does the crate move because of the rope pulling on it? Yeah, it moves up, but it moves, right? So yeah, this is work. The crate has more gravitational potential energy because of what we did to it. Also, we've applied a force, and it moved because of that force. Gravity is weight. Weight is the force that gravity pulls on it. Mass is something different. We'll get into that distinction a little bit later on. So, yeah, weight is a force. That's how hard gravity pulls on it. Mass is like what makes up that object. Okay. So yeah, we'll get into that. We'll get into that distinction later on. All right. Good with this picture. Okay? So either one of those definitions we can use to explain that work is being done. Okay? Good? Ready for the next one? All right. Here, I know not all of you play baseball and not all of you lift crates, but I figure the next picture is one that that a lot of you could probably relate to. So sometimes you just have a stressful day, you know, and you just have to go home and you have to like sculpt something out of marble, you know, just to relax a little bit. Get out your chisel. Yeah, you know. But sometimes you just can't find your little 2-wheel dolly to move your big block of granite around, you know. So you just lasso that bad boy and try and drag it across the room, you know. So, well, it's one of those 2-wheeler things that you can like lift it and drop it down, you know. What? So, yeah. So, I mean, how do you lose it? Is that what you said? Yeah, I know, but. Sometimes, you know, you just have a rough day, you know, and you're just like, I don't know where, I can't remember where I put this block of granite, so I really want this one over here though, so I'm just gonna lasso it and drag it across the room, right? So. All right, and then sometimes, you know, your day's just been so bad that you lasso your big block of granite, right, or your marble or whatever, you know, you're sculpting that day, you know. Sometimes you might be into like copper sculpting, you know, you want to make it more metallic, you know, just whatever you're feeling like that day, right? I mean, you know, maybe you are sculpting a refrigerator out of marble, like, you know. So yeah, I mean, you know, maybe that's like the beginner, you know, because it looks like a refrigerator already. So like, you know, your first sculpture, like, hey, just turn this block of marble into a refrigerator. Go, like, you know, that's like day one of sculpting school. So, but alas, you lasso your big block of marble, you pull on it as hard as you can, and it just doesn't go anywhere. And I know. So now, not only did you have a bad day at school, you can't even sculpt in your favorite sculpting location. It's just. No. The light is better over there. You can't just move you can't just sculpt over here. The light's better over there, right? But hopefully you can. I know that you all have experienced this before, so you're probably feeling like a lot of deep-seated emotions right now. Yeah, like hopefully you can look past that and answer this question: is this work when you pull on this big block of granite and it doesn't go anywhere? Is it hard work to do that? Yes, but is it work by the definition? No, right? So there's two ways we can do this. One, even though we've applied a force, does the block go anywhere? No, so there's no distance. The other way we can look at it, does the energy of this block change because of what you did to it? Does it go any faster? No. Does it go any higher? No. Right? All of the force that you've put into it doesn't change the energy, so it's not work. Right? So either one of those two ways is a good way of explaining that this isn't work. One, we don't change the energy of the object, or two, there is no movement. Huh? Okay, good. All right, next picture. Again, you know, trying to keep it relevant for you guys, right? I know this probably happens a lot to you guys on the way home, right? Giant boulders just start chasing you, like Indiana Jones style, you know, like. So.
You could always go sideways.
That's, well, you know, we start talking about things in one dimension, so you got to go forward and backwards. It's easier that way. So. All right, but you've timed it out. This has happened to you so often that you know exactly how far you need to run before the boulder will eventually stop and not run you over. I mean, that's how good you've gotten in this situation, right? So, let's talk about this boulder slowing down and eventually coming to a stop. Is work being done on this boulder as it's slowing down? Yes. Okay? So first let's talk about it from an energy standpoint. As it's slowing down, what's happening to the kinetic energy of this boulder? It's decreasing. So the energy is changing, that means work is being done. Okay, just, what do you think we call this kind of work if it decreases the energy of something? That's what happens to the boulder. Let's talk about the work. That's what happens to the boulder. What kind of work? Work is a transfer of energy. It changes the energy. So if we're decreasing the energy, what kind of work would we call this? Get closer. Okay? This is work because the boulder is losing energy. So if we decrease the energy of something, we call that negative work. What's causing the boulder to slow down in this case? Friction, right? So, Lindsay, if we want to slow something down, which way do we have to push on it, or which way do we have to apply our force? The opposite direction. That's why it's negative work. Because we're pushing on it, we're just pushing on it in the direction opposite of the way that it's moving. That's the negative part, right? So, my base, sorry. Oh, there it is. My base. I was looking for my baseball. So, here, I'll do this. Lindsay, do you feel confident enough in your ability to catch this tennis ball if I toss it to you? Okay. Anybody? Anybody? All right. So, okay. Okay. I'll toss it to you. Okay. Right. Ready? Here we go. Okay. So I toss the ball. Ethan catches it. Okay. Here, let's do something. Okay. So let's go try and catch it at approximately the same height that I throw it from. Okay. Approximately. Okay. Did I do work on the tennis ball when I threw it? Yes. I did positive work because I increased its energy. I increased its kinetic energy, right? I also kind of threw it up in the air, so I maybe increased its potential energy a little bit as well. When Ethan caught it, what did he do to the energy? He did negative work. How much negative work did Ethan do? An equal amount of negative work to the amount of positive work I did in starting it to go. I increased the energy, Ethan decreased the energy. But if we end up with the same amount of energy, now we've each done the same amount of work. In order to stop the ball, what does Ethan's hand have to do to it? Apply force, but which way? The ball's moving this way, so Ethan's hand has to push on it in the opposite direction to get it to stop. That's the whole negative work idea. Does that make sense? Okay. All right. Are we good with these ideas? We okay here? Okay. Let's go and let's take a look at the sheet I gave you today. Let's start with the ramp side. Okay? Let's start with the ramp side. You might want to keep that outline out just so we can reference it, because we're going to talk about some of the things on that sheet. Okay? All right. So, on the ramp side, there are 4 questions. There are 2 slides here, but we'll go through it, right? So, first question says, how much work was done on the ball in picture number 1? This is picture number 1, even though it's not labeled as such. Come on. Oh, it wasn't on. I had to turn it on. This is picture number 1. What? How much work was done when we lifted the ball from the ground to the top of that platform? What? 30 joules. Kendall, how do you know that 30 joules of work was done? That's like the past, you know, right? Yeah.
So the starting point of it at 0.
Good.
And then it increased in 1%.
How much did the energy change in this situation? How much did the energy increase? By 30 joules. So how much work was done? 30 joules. Okay? Because work changes energy, and the energy increased by 30. Does that make sense? You good there? The next couple of questions ask us more about potential energy than they do about work, but it's okay. So the next question says, sorry, everybody done writing? Next question says, how much gravitational potential energy does the ball have at the ramp, at the top of the ramp in picture number 2? So how much potential energy should it have up there? 30. Why? Same height. Is it the same ball? We'll assume it to be, right? So, in this case here, at the top of the ramp, on picture number 2, it should have 30 joules, right? Same height. Same gravitational potential energy. That make sense? All right. Next question says, how much gravitational potential energy does the ball have on the second step in picture number 3? Kendall. 20 joules, right? What are we assuming about those 3 steps, Kendall? They're equal height, right? We said that height affects gravitational potential energy, right? So PEG equals m times g times h. What type of mathematical relationship do all those variables have with the gravitational potential energy? We said they all have what kind of relationships? Direct relationships, right? So if the height goes from the 3rd step to the 2nd step, the energy is going to go from 30 down to 20. If we put it back up to the top step, how much energy should it have again? 30. That's the next question, right? It says, how much potential energy does the ball have at the top step? Picture number 3. No, sorry. There's a second part of this question. Right? Okay. All height is directly related to that gravitational potential energy. Okay? All right, good. So the next question is a little bit more of a preview of next week, but that's okay. If we knock the ball off of that ledge, what is it going to start doing? It's going to start falling. What's happening to its height as it falls? It's decreasing. So what's going to happen to its gravitational potential energy as it falls? What happens to its gravitational potential energy as it falls? If the height decreases, what happens to its gravitational potential energy? It decreases, because gravitational potential energy depends on height, right? So if we knock the ball off of the ledge, gravitational potential energy is going to decrease because height is decreasing. But what happens to that ball as it's falling? Specifically, what happens to the speed of the ball as it's falling? It goes faster, right? As it falls, the height decreases, but the speed increases. Yes, no, maybe? Right? If speed is increasing, what's happening to the kinetic energy that the ball has? It's increasing. When it gets down to the ground, or more importantly, right before it hits the ground, like the very, very instant before it hits the ground, what is the height? The height is essentially what? Right before it hits the ground, the height is what? 0. Or some real small number, yes? So, how much potential energy does it have when it hits the ground? None. But what is it doing right before it hits the ground? How fast is it going? Fast or slow? Fast, right? All of that potential energy that it started with got turned into what? Kinetic energy. So if it started with 30 joules of potential energy up here, how much kinetic energy should it have down there? 30 joules. You could also put it in words that you understand if that doesn't make sense to you.
Are you saying that like energy in the arrow because everything stays the same? Right?
I'm saying as this ball falls, $30 joules of potential energy that it started with up here, Yasmin, are turned into 30 joules of kinetic energy that it ends up with down there. Because right when it hits the ground, how much potential energy is left in it? When it hits the ground, what is its height now? And if it has 0 height, how much gravitational potential energy does it have? None. So all of that energy that it started with as gravitational potential got turned into kinetic energy. Okay?
What if ground level not be zero?
Ground level is a relative term. So you're right. What does that mean? Because like if I take this baseball and I go here and I lift it up and I drop it back here, that's great, but what if I start it on the ground, right? That is a relative term. And what we find out even is that it doesn't actually matter what we call zero, how much the potential energy goes up and how much it comes down by holding it this high versus this high. The number might be a little different, but how much it goes up and how much it goes down actually stays the same. The change in the potential energy actually stays the same. All right, we okay with this? Yes, no, maybe? Yeah. Let's call it a day. That's good for now. We will maybe visit some of those car pictures on Monday. There are some questions on the quiz that do relate to the card picture, so you might not be able to do the entire quiz. You might want to hold off until Monday night or Tuesday. Okay?